Now we're given another situation here, and I kind of messed this up in class by being a little careless with what I wrote down, so I apologize for that, but I made a couple of corrections and it came out all right. Okay, we have an acceleration of 10 meters per second squared. Now that could correspond to a falling object where the downward direction is positive and the acceleration of gravity is 10 meters per second squared. Now I could say 9.8 meters per second squared. If you're taking your engineering dynamics course, you're going to want to use not just 9.8 meters per second squared, but probably 9.81 or 9.806 or whatever it happens to be at a particular specific place. Because if you're engineering something, you want a sufficiently precise result. So you assume that you want to use a fairly accurate acceleration. By using 10 meters per second squared, I'm about 2% off. And calculation gets much easier. You can see the procedure without worrying about the square of 9.8 or multiplying 9.8 by different numbers. Easy to do that. Multiply 9.8 by something, multiply it by 10, then subtract 2% of that. And you should be able to do that in your head. Okay. Anyhow, the other thing is that at some time t, well, at a certain time, this thing is at 3 meters. So at x of t is 3 meters. And then 0.24 seconds later, it's at 5 meters. That means after some time that we don't know, it has fallen 3 meters. And 0.24 seconds later, it's fallen an additional 2 meters. Meaning it's moving pretty fast. If it falls 2 meters in a quarter second, that's about 8 meters per second. So it's been falling, for a good fraction of a second. Now let's assume that V0 was 0, okay? So we don't know what t is, but we know that V0 was 0. And what we want to do now is get our position function. So we take the information we have. X of t is x0 plus V0 t plus 1/2 at squared. Okay, and that has to be 3 meters. Well, if V0 is 0, the V0 t term isn't there. We're just left with the x0 and the 1/2 at squared, and that's what we have here. Half of the 10 meters per second squared is 5 meters per second squared. It's that times t squared, and that has to equal 3 meters. That would seem like we've only got one unknown then, and we should be able to find x0. The problem is we don't know t, so t is also unknown. We don't know what t was when this thing hit 3 meters because we don't know how far above this point it was when it started. We know it was started from rest, but we don't know how far. So we're going to have to figure that out, meaning we're going to have to figure out what x0 was. Okay, now at t plus 0.24 seconds, 0.24 seconds later, the thing's at 5 meters. How do we represent that? Well, if x of t is x0 plus V0 t plus 1/2 at squared, which is what it always is if we have uniform acceleration and use this form. Again, V0 is 0. We don't have a V0 term. We just have the x0 plus 1/2 a, which is your 5 meters per second squared, times the square of the time. What's the time? Well, now it's t plus 0.24 seconds. Okay? So really, and I guess I'll write it out, x of t, writing kind of small because you've seen it before. Okay? If x at t plus 0.24 seconds is equal to 5 meters, well, x at t plus 0.24 seconds is the expression you get when you plug V0 equals 0 in here and plug t plus 0.24 seconds in for t. That's how function notation works, and I'm sure you're fine with that, but I want to emphasize it. Okay, so now we have this equation. Now we have two equations in two unknowns. There are many ways to solve it. These are not linear equations, so we want to be a little bit careful. We can't use matrix reduction, at least not in the way you're probably used to using it, in order to solve a pair of nonlinear equations. Again, our unknowns are x0 and t being squared. We're not linear. Okay, So to solve these equations, there are a number of things we could do. We could solve this equation for t and plug that in for t up here. And our result, the resulting expression would have only x naught as a variable, having solved this one for t. And then we would only have one variable here. We'd be able to solve it. We'd probably have a quadratic equation, if not worse. But we could do that. Or we could solve this equation for x naught, and that would be pretty easy to do. We get 3 meters minus 5 meters per second squared times t squared, plug it in here, and now we just have one equation in t. And that equation appears to be a quadratic equation. What I'm going to do instead is I'm going to subtract this equation from this one. Okay? If I subtract this equation from this one, that eliminates x naught. Now the two ways of solving it that I mentioned are perfectly valid. There's no reason you couldn't do either of those, and they would be perfectly legitimate solutions. So this is just another solution, and it's the one I chose. If we write these down like this, it's very clear that if I subtract equations, x naught goes away, and we're just left with t. And let's see, 5 meters minus 3 meters is 2 meters. Now we've got a 5 meter per second squared common to these two terms, so we're just going to write 5 meters per second squared times the t plus 0.24 seconds squared minus the t squared. If that's not completely obvious to you, it's not completely obvious that that's a valid step, write it out carefully, because you really do need to put your algebra on the firmest possible foundation, and I don't think that would particularly challenge you, even if you don't see it, and you probably do. Okay, well, that's something, but what are we going to do with that? Well, we're going to probably expand this and see what we've got. Okay, expanding t plus 0.24 seconds, quantity squared. Now don't make the mistake that people should not at all be making at this stage of their mathematical education. Having had a year of calculus, don't think that the quantity t plus 0.24 squared is t squared plus 0.24 squared. I still see that. And you know, it's easy to write that down if you're not thinking. All I'm saying then is make sure that you're thinking, and don't shortcut things unless you're really confident. Okay, that's a binomial. I've got to square it. I'm going to get a t squared. I'm going to get 0.24 seconds squared. I'm also going to get 2 times this times this. If you square a plus b, you get a squared plus b squared plus 2ab. And you got to have that 2ab term in there. That 2ab term would be 2 times this, 0.48 seconds times t. And then we're going to have a t squared from here. This t squared is going to subtract, so you're going to get rid of the t squared, which is nice because the equation looked like it was going to be quadratic, and all of a sudden it isn't. That's very convenient. If you square 0.24, you get 0.0576, unless I'm completely off my rocker. I know that 0.25 squared is 0.625, and if you subtract half from that, you get 0.575, and you get that extra 1 because of the square of the a minus b. And if you understand that, great. If you don't, well, kind of wish you did, but it's not required. Okay. Now, what do? A couple of things I could do. I could divide by the 5 meters per second squared if I wanted to, but instead I'm going to just expand this. Just use the distributive law. And you can verify that if I distribute this through here, I get something very much like this. Then the solution, because I was debating about whether to say how I got that. This is an approximation. And it's somewhere between 0.28 and 0.29 meters, I think. But verify my approximation there. I'm just trying to show you how the solution goes, and I'm not going to get too meticulous with the numbers. If I subtract the 0.29 meters from both sides, I get 1.71 meters over here. I'm going to divide that by 2.4 meters per second squared. And I got a little question mark. I think that's about 0.73 seconds. Okay, so we determine that the object is here after 0.73 seconds. Now what we want to do is we want to get the constants here. Now, we know V naught, we still don't know X naught, but now if we plug in 0.73 seconds for T, we should get 3 meters. Because after 0.73 seconds, this is supposed to be at 3 meters. So we say X naught plus 5 meters per second squared times 0.73 seconds. That's our left-hand side, remembering the V naught is 0, is equal to 3 meters. Okay, well, multiply this out, subtract from 3 meters, we get something like 0.5 meters. Now you can refine that. You can see how much error there is in my estimate. It might be a huge error. I think it's pretty close though. Okay, and then we determine that our function is x of t equals 0.5 meters plus 5 meters per second squared times t. If the question is, where did this thing start? Well, it started at x equals 0.5 meters, x being along this axis. I might have used y, since y usually refers to vertical, but I used x to be consistent with what we have here. We could call the variable aardvark if we wanted to, it wouldn't matter, as long as we're consistent. Anyhow, okay, it's at 0.5 meters here, 0.74 seconds later, it's here. Now, at t equals 0, it's at 0.5 meters. At t equals 0 is at v naught. So the point from which it fell was at 0.5 meters. This point is at 3 meters, so it must have fallen 2.5 meters between 0 and 0.73 seconds, meaning it started 2.5 meters higher than this. Okay, so it has fallen 2.5 meters to get to here, then it falls the rest of the way. And this can be adapted to the flower pot problem. Flower pot falls from some point higher, and you observe that it passes a certain window in 0.42 seconds, I think was the number. And I used 0.24 seconds here, kind of in reference to that. You can solve that problem by this method. There's other ways to solve it. There are other ways to solve it. But the idea of getting the position function and then dealing with that is really quite powerful.